Hello, welcome back for lesson 4.2, and we are going to dive into these linear relationships and formalizing an equation, a linear equation, a y equals mx plus b. In our case, it's going to be a y equals b plus mx, or ax. It's just a letter that you're giving for this thing called a slope and y-intercept. But it's going to be basically like a recipe that you can use to take this explanatory independent variable and lead us to the response or dependent variable. And we're going to use a state crunch to do that today. So let's go ahead and turn in our course packs to page 116. And we're going to call this thing, this equation, this linear equation. It's a least squares regression line. That's what you're going to see in my stat lab for the assignments. Sometimes you'll see it called the line of best fit, the trend line, the linear model, the linear regression model, the regression line. It's a straight line that best fits a bivariate, two variable data set. Okay. This is our slope, is A. Okay, it's how the variables change. And sometimes in StatCrunch, it's going to be actually this B will come first, and then it's the slope times the independent variable. So the slope is the A, sometimes it's the M in the equation. The slope is the ratio of the change. And when I say change, it's the change in the y versus the change in the x. Slope is a measure of steepness. It can be written as rise over run. Sometimes they write that. Sometimes they calculate it as y1 minus y2 over x1 minus x2. We use this delta x over delta y. Delta means change. So as your x is increasing, what's happening to y? So in this case, y is also increasing. Okay. The interpretation for the slope, this is on your your yellow sheet here. Here on your yellow sheet, the interpretation of your slope or your interpretation. So it's on average if x. So when we say x, we mean what does the x represent? What increases by 1? So if x increases by 1, y is expected to increase or decrease by approximately a. So when we say increase or decrease, that means if your slope is positive, you're going to use the word increase. If it's negative, you're going to use the word decrease. Okay. Then the y-intercept is the b. It's this point right here, and x is 0, y is whatever this b value is. It's your starting value. So the y-intercept is where the least square regression line intersects the y-axis. The y-intercept is the value when x equals 0. There's an interpretation for the y-intercept. It's when x is 0, y is expected to be approximately b. So remember, when we put x and y in quotes here and up here, I want you to actually give me in words in the story, what does x and what does y mean? Okay. And so down here, we say that x means and y means. X means the explanatory variable, and y means the response. variable. Okay. So let's just kind of refresh slope and y-intercept and all those good things here on page 117. It says, consider the following linear graphs for y equals ax plus b. Assume all are drawn on the same scale. Label the sign of a, which is the slope, positive, negative, or 0, and explain. So let's go through each of the four. So the slope on each. So the slope here is positive. It's going uphill. It's actually very steep and going uphill here. And 3 and 4 is going downhill. And so how we find that is as we're moving from x from left to right, what's happening? So starting at the very left point and going to the right, it looks like it's going down. So slope is negative. And here's the same way. It's very steep, so it's hard to see. But if you look to the very furthest left, which would be here, and we're moving very slowly right, it's definitely going down. It's very steep. And then it says label the b, the sign of b on each. Is it positive, negative, 0? Okay. So I'm going to do that in my red color. And b is the y-intercept. So here is b. And because it's above 0, it's positive. B is down here. B is negative. Here's B is always where it's crossing the y-axis. So here's B. B is positive again. And oh, right here it looks like B is exactly at 0. So C says, which graph has the steepest slope? So the one is that's closest to going straight up and down. Steepest is like you're climbing up a stairs. And sometimes it's just like walking up a ramp, very shallow. Sometimes it's like feeling like you're going straight up a mountain. And I would say that's number 4. This is the steepest. Which graph has the largest y-intercept? So the largest y-intercept would be the highest on the y, and that would have to be number 3. This has the largest y-intercept. And it's highest on the y-axis. That's how we know it's the highest y-intercept. Okay. Sometimes you'll be given data in a scatter platform like we did here, and we'll give you the linear equation or line of best fit. We did that here. So be looking. Sometimes if you don't have a table of data, sorry, it's because it's given to you on the graph. So be looking all over. So always think outside the box. So here we gave you the equation in the y equals mx plus b form. So this, or ax plus b form. So this is ax plus b, y equals. It says, explain the meaning of the slope of the line in the context of the situation in the story. So I want you to use this interpretation right here on your yellow sheet. Okay. So I'm just going to write my slope over here. My slope A is equal to the value that is attached to X. Okay, always include the X and the Y in your, when I ask for the linear regression equation. So here it is, negative 4.6711. So we are going to use this interpretation here, on average, comma, if. On average, comma, if, and I'm not going to write X, I'm going to write, what does X mean in my story? X is my fertility rate. We're going back to that data that we talked about in 4.1. So if the fertility rate increases by 1, I'm just copying what's on here, on average at X, or the fertility rate increases by 1, comma, Y. So my Y is life expectancy, so comma, life expectancy back here, is expected to, and mine is a negative, so I'm going to use the word decrease, is expected to decrease, is expected to decrease, again, because my slope is negative, I'm using the word decrease, by approximately, and then whatever my slope is. And you're not going to write negative because we've already used the word decrease to talk about negative. We're just going to write 4.6711, and then we have to use units, which is years. Okay, so on average, if the fertility rate increases by 1, and we really should have units here, birth. Life expectancy is expected to decrease by approximately 4.6711 years. Now, the y-intercept. It says, explain why the y-intercept does not make sense in the context of the situation. I need to know what the y-intercept is before I can explain why it doesn't make sense. So the y-intercept is 0, comma b, which is 0, comma 81.51. And so go to your yellow sheet and let's use that to explain, interpret. We're not going to interpret it, but we're going to figure out why does it not make sense to have 0, comma 81.51. And the reason that this doesn't make sense is that if we don't have any birth rate, so if a woman, if the average woman doesn't have any children, they're going to live to be 81. That seems interesting. Just because the average is 0 births, which is not likely for a country to have this, right? There aren't any countries in the whole world that have an average birth rate of 0 births, so that's not likely. C says the United States had a life expectancy of 70.21 years in 1962. Calculate the expected fertility rate back then. So they had a life expectancy. That means this is Y, and they want to know X. Okay, so we're going to use the equation that we were given. So Y equals negative 4.6711 X plus 81.51. We know Y is 70.21. And we need to solve for X. So to do that, we are going to subtract 81.51 from both sides because that's how we solve an equation for X. So on the right, we still have negative 4.6711X that we're trying to solve for. And then we have here 70.21 subtracting 81.51. We have a negative 11.30. And now to solve for X, we're going to divide both sides by a negative 4.6711. And we have a negative divided by a negative, and this comes out to be approximately 2.42 births. So X is approximately, right, because they're all rounded, 2.42 births per woman. So D says, suppose that in 1962, a country had a fertility rate of 4.54 births per woman. Using a linear equation given on the graph, what would we expect that country's life expectancy to be? Okay, so they gave us the fertility rate this time. And so we can just put 4.54 births per woman in for X. And you can do this in Desmos if you'd like. Or you could do it on a TI-84 calculator or on another calculator. And I like Desmos because it's very handy to use. So I can say negative 4.6711 parentheses 4.54 parentheses plus 81.51. Don't forget you have to add on that y-intercept. So the whole equation. And it says that the life expectancy would be approximately 60.303 years. It says Gabon had a birth rate of 4.54 children per woman and a life expectancy of 39.56 years. Okay. Compute, draw, and label the residual. Okay, residual. So Gabon, let's go back to our scattergram and see where Gabon is on that scattergram. Gabon had a birth rate of 4.54 women. So right about here, and a life expectancy of 39.56. Yep, just under 40. So this is Gabon. So the residual that we're going to calculate is the difference between this actual value here, this 39.56 years, and the actual life expectancy that their actual was a 39.56, and then we want to take the difference between that and the predicted. So the predicted value is what's on the line, which I'm guessing is going to be just above 60 here. So we need to find that. This is our residual. Let's go back to the formal definition down here. Residual or error is the observed y. So that would be 39. So residual is the actual or observed, 39.56, minus the predicted. Okay, well, we just predicted it's 60.303 up here. 60.303. Okay, so that comes out to be a negative 20.74. So negative 20.74. That means the actual was under. So we over predicted. Oh gosh. And let's talk about that down here. Residual has the same units as our y values. The least squares regression line is a linear model that makes the residuals as small as possible. So they came up with the best line possible. This line right here, this equation is the best possible that the calculator could come up with. And Gabon has a very big residual. So we definitely, our predictor either way over predicted, which we did, or maybe Gabon is just an outlier. And we're going to continue to talk more about outliers this semester. Okay, so a positive residual means we under predicted. And a negative residual means we over predicted. So we definitely over predicted on this one. We predicted their life expectancy would be 60.3 years when really in actuality, a woman's life expectancy is only just under 40 years in Gabon. Interpret Gabon's residual value in the context of the situation. Was it doing well or poorly in 1962? Gabon with a life expectancy of 39.56 years was 20.74 years under the predicted value of 60.3 years. Okay, so this means that they lived much less than what they were expected to live, many fewer years. So they were doing poorly. Gabon is doing poorly back in 1962. Okay, so let's talk a little bit more about Gabon's prediction here. So making our prediction for Gabon's life expectancy is an example of, okay, this is called interpolation. Interpolation is using the regression model to make predictions for X values that are among those observed in the given data set. And Gabon was observed in the given data set. So this is an interpolation. It's interpolation. Extrapolation is using the regression model to make predictions for X values that are higher or lower than the observed in a given data set. Outside the scope of the model, do not use the regression model to make predictions for values of the explanatory value X that are a lot higher or lower than the observed data from the given data set. Okay, so you don't really want to go, outside of here. Okay. Suppose we find out a country in 1962 had a fertility rate of 9.3 births per woman. Explain why we should not use our model to make a life expectancy prediction for that country. Okay, because our maximum births per woman was just over 8. So we shouldn't make any predictions outside of 8.5. It is outside the scope of our data. We only had X values just over 8 births. What would be a low X value we would not want to use to make predictions? So just over 8 was the highest, and then just under 2. So maybe 1.8. And then this just says sketch a graph to illustrate this joke. Why is that woman scowling at me? Do I know her? It says if she loves you more each and every day, by linear equation, she hated you before you met, right? So that means that she's going to continue to love you. If you look back here, she must have not loved you, right? When you didn't know her, which doesn't make sense. So let's for a minute go back to the data that we worked with on the free and reduced lunch. Here is the scatter plot, and we have it pulled up as well in StatCrunch. So let's go back to that. Okay. So here's our StatCrunch. Here it matches what we had on the screen here. And it says compute the line of best fit, letter A. So we can hover over and it gives us the line, okay, which is y equals 69.108. Minus 0.2 let's hover over that, and I'm going to show you how to find it this way too. Negative 0.2826 x. So let's go do two things. Let's practice getting the scatter plot, the graph. So we're going to go to scatter plot down here, graph and scatter plot. And then our x variable is the free lunch. The y variable is passing math. And then we're going to click on overlay polynomial order 1. And then just leave it at best fit. That's all you have to do, and hit click. And there's your scatter plot. And if you hover over the red line, it gives you the equation in the y equals b plus ax form. Remember, it always gives the y-intercept first. Now, we can also go to stat and regression and simple linear. That's another way. This takes a little bit longer, but free lunch, passing math, and then all you have to do is hit compute. And this gives it out in a table form. And remember, it is going to give the dependent variable, passing math, independent variable, percent on free lunch. And then here's your equation. It's not going to use y and x. It's going to use the variables. Okay. So let's go back to our paper for momentarily. And it asks us to explain the meaning of the slope of the line in context of the situation. Okay, so our slope A is negative 0.2826. And so remember, we are going to use our interpretation on the paper, on the yellow sheet. It says on average, comma, on average, comma, if percent of children on free lunch increases by 1%, make sure you have units on there, comma, y, which is percent passing math, is expected to decrease, because it's negative, right? We're going to use the word decrease, by 0.2826%. So again, we're using what's on the yellow sheet. Letter C says, interpret the y-intercept in the context of the situation. Does it make sense? Is it outside the scope of the model? Okay, again, we're going to the yellow sheet. Our y-intercept is 0 and b, so in this case it's 0 and this 69.108. And the interpretation says when x, which is the percent of children on free lunch, is 0%, comma, the percent of children passing math is expected to be approximately B, which we're going to write 69.108%. Okay, the interpretation is right here on your yellow sheet. Always be sure to include units in both your slope and your y-intercept interpretations. Those are very, very important. Okay, so now let's use our equation to answer some questions. So D says the nearby Amber High School has, oh, you know what we didn't ask is we didn't talk about the scope, did we? Does this make sense? Well, it doesn't make sense that you're ever going to have 0% of students on free lunch. Probably not likely. But is it outside the scope of the model? And yes, it's outside the scope because we don't have any schools that have less than 15%. So let's just make a note. Outside scope because we don't have Any schools with fewer than 15%. Okay, so that's important to note. It's outside the scope. So our scope should be here within there. Okay, so we have the student, there's a nearby high school called Amber High School. It has 40% of their students on free or reduced lunch. What percent does the least squares model predict pass the math test? Okay, that is negative 0.28. Okay, so full equation here. Negative 0.28. 26 times 40, and we're not going to put it as 0.4 because the data came to us as whole percents. Okay, so we're going to use it as 40. Plus the slope of, or the y-intercept of 69.108. And we can put that in Desmos. And negative 0.2826 plus 69.108 is equal to 57.804 percent passing math. That's what we're predicting from the least squares regression line. And let's go back and write that down. So that's what we predicted. So it says, is Amber High School outside the scope of the data? Well, Amber High School 40% passing math is inside the scope, right? That would be, this is all inside scope. So inside the scope of, so the smallest we have on free and reduced lunch was 15% up to the highest was 60. So right in the middle. Determine the residual for Amber High School if they actually had 65% of their students pass math. Woo! So residual was they actually had 65 minus what we predicted, 57.804, which comes out to be a residual of, what is that? 7 point, let's see here. 65 minus was 7.196. That's our residual. And so let's interpret what that means on the residual. So it's positive. So we underpredicted. So we underpredicted, which means that Amber High School, Amber outperformed what we predicted. Amber outperformed what we predicted. They are doing well. That's exciting. Now remember, not every context that you look at is going to be if you under predicted it, they're doing well. So you have to look at from context to context what is the interpretation. Suppose a local private high school wants to use the least squares regression model to make predictions as well. Why would this not be appropriate? Well, we would never compare. We would never compare private high schools to public high schools. Schools to public. Because private schools are less likely to have as many students on a free or reduced lunch than a public school. So you're not really comparing apples to apples. So not a good comparison. Would not recommend that. So this is the last of chapter 4.2. Catch us back for 4.3. We're going to build on this. We're going to go from our scatter plot and correlation coefficient to our linear regression equation in 4.2 to our R squared in 4.3 and our residual plot. And we're just going to expand on this and the chapter in 4.3. So catch us back.